In all of chemistry, there's this one idea, this one concept that kind of acts like a universal translator. It connects the invisible world of atoms with the world we can actually see and measure. It's called the mole, and honestly, understanding it is the key to unlocking how we build pretty much everything, molecule by molecule.
Think about it like this. Imagine you're trying to bake a cake, but your ingredients, the flour, the sugar, they're all so tiny you can't even see them, let alone count them out. That's basically the challenge chemists face every single day with atoms and molecules. So how on earth do they pull it off?
Get a load of this number. That is roughly how many H2O molecules are packed into a single drop of water. I mean, you could never, ever count that high. It's a number so huge, it's almost meaningless. And that is the core problem that chemists had to solve. Because look, to make anything useful, from life-saving medicines to brand new materials, scientists can't just toss things together and hope for the best. They need to be precise. They need a way to count the uncountable.
And that brings us to the hero of our story, the mole. And no, not the little furry guy that digs up your backyard. In chemistry, the mole is this absolutely ingenious counting tool. It's a concept that lets chemists work with atoms just as easily as a baker works with cups of flour.
And the core idea here is actually really simple, because we use this kind of thinking all the time, right? If I say I have a dozen donuts, I mean 12 donuts. The mole works in exactly the same way. It's just a convenient name for a specific and, yes, a very, very large number of things.
And that magic number, it has a name, Avogadro's number. It's 6.022 times 10 to the 23rd power. So 1 mole of carbon atoms is just Avogadro's number of carbon atoms. 1 mole of water molecules, you guessed it, Avogadro's number of water molecules. It's this perfect, universal standard.
Okay, so we can count particles in theory. That's cool. But the real power, the genius of the mole, is how it builds a bridge from that invisible world of atoms to the world we can actually see and measure in a lab.
And this bridge is called molar mass. All it is the weight in grams of 1 mole of something. And here's where the magic happens. If you go into a lab and weigh out exactly 18 grams of water, without having to count a single thing, that you have precisely 1 mole, or 6.022 times 10 to the 23rd molecules of H2O. No counting required. It's amazing.
All right, let's make this real. Using what we just learned, how would we figure out how many moles are in, say, 9 grams of water? This is a super common problem in chemistry.
It's really just a simple 3-step process. First, you start with what you have, which is 9 grams. Then you use what you know, that the molar mass of water is 18 grams per mole. And finally, you just divide the mass you have by the mass of 1 mole.
So 9 divided by 18, that gives us our answer, 0.5. 9 grams of water is exactly half a mole. And just like that, we've translated a weight we can measure on a scale directly into a specific count of molecules. See, that's the power of the mole.
But wait, the mole's translating power doesn't stop there, not at all. It also builds another bridge to a totally different kind of measurement, one that's really important for gases, volume.
Okay, remember this number, 22.4 liters. I know, it might seem kind of random right now, but trust me, in the world of chemistry, especially when you're working with gases, this number is a huge deal.
And here is why that number is so cool. Under standard conditions, we're talking a specific temperature and pressure, 1 mole of any gas, doesn't matter if it's super light like helium or heavy like carbon dioxide, it will always fill up the exact same amount of space, 22.4 liters. It's another one of those incredibly useful shortcuts.
Okay, so we can translate moles to mass, we can translate moles to volume. Now it's time to put it all together and see the ultimate application, using moles to read a chemical recipe and predict exactly what's going to happen.
This right here is the chemical recipe for making water. Those big numbers out front, they tell us the proportions, the ratio. So this reads, for every 2 moles of hydrogen gas that you react with 1 mole of oxygen gas, you will get 2 moles of water. It's a recipe.
All right, now for a classic chemistry puzzle. What if you don't have the perfect recipe amounts? Let's say you've got 4 moles of hydrogen, but you've still only got 1 mole of oxygen. What happens then? Which ingredient is going to be your bottleneck? Which one runs out first?
So to find that bottleneck, we do a really quick calculation for each ingredient. It's simple. We just divide the amount of moles we have by the amount the recipe needs. So for hydrogen, we have 4, the recipe needs 2. 4 divided by 2 is 2.
For oxygen, we have 1, the recipe needs 1, 1 divided by 1 is 1.
Now here's the key, and it's super easy to remember. The ingredient with the smallest result wins, or, well, loses, I guess. It's our limiting reagent. Since oxygen's ratio was 1 and hydrogen's was 2, oxygen is the one that's going to run out first. And the second it's all gone, the reaction just stops, dead in its tracks, no matter how much extra hydrogen you have lying around.
And because that oxygen runs out, it gets to decide the final outcome. Our 1 little mole of oxygen, following the recipe, lets us produce a maximum of 2 moles of water. We've just used a mole to predict the exact amount of product from a chemical reaction. How cool is that?
So you see, the mole is so much more than just some gigantic number. It's the translator. It lets us speak the language of atoms. It's the tool that lets us take a recipe written in symbols on a page and turn it into a real substance in the real world. It gives us the power to actually build our world molecule by molecule.
By understanding the mole, you're not just learning some abstract concept. You are learning the fundamental language of chemistry, the language that describes how absolutely everything around you is made. So I guess the only question left is, now that you can speak the language, what will you create? Thanks for tuning in.